Alright, hell yeah. So we have physics for scientists and engineers. This is Saraway Jewett, and this text is available on a PDF. Maybe I'll put that in the description. So what we have here is, this is the chapter on velocity. Even though we have a dog's hair that is growing, you can think of the dog's hair as like a car that's just moving really slow. And I think you should do that because anything that you use speed, like driving in cars, we're pretty good at. Okay, so I'm going to go over the technical solution. This video got away on me because we have a combination of units. We have a velocity in millimeters per day. I think we can handle that. Millimeters like very small amount, but every day you're going to increase by that much. You know what I mean? Might be 10 days to get a centimeter. Okay, so now we have some understanding of maybe how a dog's hair is growing. Okay, so hell yeah. And then this problem does say we have an acceleration, and that's a change in velocity. So our velocity of the dog's hair is 1 millimeter per day on average, and we're going to increase this by 0.132 millimeters per day. But we're going to do that every week. You know what I mean? So I kind of got confused even, and and be like, well, is my velocity increasing by 0.1 every day? Like by day 2, is it 0.1? No, it's not. In 1 week, my velocity is going to be 1.1. And then in 2 weeks, it's going to be 1.2. You know what I mean? And so it's good to also have just an idea of how to kind of ballpark a question. Now, we're going to go over the technical solution to this. Using integration, we start with acceleration, and we see that acceleration is a derivative of change in velocity, change in time. So anytime you're working with acceleration or even just velocity, you want to write both these equations down. Acceleration is dv dt, and velocity, and just say it out. Velocity is the change in position, change in time. And then I would write kind of its cousin equations, where this is kind of the differential, where your mind melts because your change in time is just really, really small. And so I like to write these ones down as well. Using a caret, a substantial, so if you change time, you know what I mean, hey, my velocity is going to change by this much. You know what I mean? So, this is change in velocity, change in time, definition of acceleration. This is just the average acceleration. So average velocity is change in position, change in time. Okay, now the kicker on this problem is to change the units like right up front. And we go to the question. The question wants to know how much will the dog's hair grow during 5 weeks. So we want an equation where we plug in t is equal to 5 weeks. So we want an equation for position, something 5 weeks, and that's going to pop us out millimeters. So that's kind of what we're shooting for. Alright, so that means that we have to take this acceleration equation in millimeters per day per week and make it all in weeks. So this days is the one that's kind of off. So we have millimeters per day. We need to multiply this by something to change it to weeks. So we multiply it by a unit conversion. We know that 7 days is the same length as 1 week. So we stack this ratio and we cancel this d. So this d is on the bottom, this d is on top. 7 days is equal to 1 week. And then we gain, this unit. So now this becomes millimeters per week squared. We multiply these two numbers by 7, and we get an acceleration of 0.924 millimeters per week per week. I always write acceleration like this, even though it has your time value. You know what I mean? A lot of people would write it like this, millimeters per week squared. If you write it like this, you can say it out. This is a change in velocity of 0.924 millimeters per week every week. And I think that's a very useful thing to do. Okay, so now moving on to our velocity. It's 1.04 millimeters per day. We need to do that same ratio, cancel days, and multiply by 7 days in 1 week. We get 7.28 millimeters per week. Cool, so we're almost growing a full centimeter every week. And so like right here, you can just kind of guesstimate, Well, if I'm growing a centimeter a week, maybe I'll grow 5 centimeters. You know what I mean? 50 millimeters. And that's kind of very close to what the answer is in the end anyway. So always be, be eager to be in guessing mode, because that can help you, if you mess up the details. Okay, I'm gonna go over this because I think this is one of the things that can be the most confusing. Of like this confused me all the time. Okay, so I have this value for acceleration. It seems like this is just a value, and then I have this value for velocity. It seems like, you know what I mean? Like I get confused of what's a value and what's an equation. So we're going to take a look at that right now. So up here, we solve for this 0.924 millimeters per week. This is an equation, but it's also a value as well. So when your acceleration is constant, it's fascinating. I can say, what's my initial acceleration? Well, it's 0.924. What's my final acceleration? Well, it's 0.924. It's a constant. Your acceleration doesn't change for this problem. So I can say my acceleration final. And so here's the different ways that you could write it. You know, sometimes you'll see in kinematics, you'll have this AI, acceleration initial. That's the same thing as acceleration bracket 0. And this bracket 0 is the same thing as acceleration bracket t is equal to 0. It's the same thing as bracket or acceleration and then just t is equal to 0. It's the same thing as writing over here at t equals 0. You know what I mean? Acceleration is 0.924. Kind of all different ways to write the same thing. And then at t is equal to, I don't know, 5 weeks, acceleration is 0.924. So there you go. So that's just all the ways to write the same thing. And like this also, this is an acceleration. So writing it as a function, and this is a function of time. And so one of kind of the mental tricks that I do is just throw a t to the 0 here. Because even if I throw in time is equal to 0, well, that's the only one that's going to be nonsensical. But if I throw in time of like 1 week, hey, 1 to the 0 is 1, and this value of acceleration doesn't change. If I say 5 to the 0, that's 1, and this value of acceleration doesn't change. So I find that a useful thing to do, is especially when I have a constant, always be reminding myself, is this an equation? And is it an equation? Is it an equation is a function of time? And I kind of go over that in kind of the main video as well, just briefly. But now let's go over here to what is not an equation. Here it says, and especially like the word now, it says now, right now our velocity is 1.04 millimeters per day. And so we changed that to 7.8 millimeters per week. But this is our initial value on velocity. So I specifically wrote over here, velocity as a function of time is not equal to 7.8 because this velocity is going to change. So I think that is kind of important. So rewriting this would be, at t is equal to 0, velocity is 7.28. Okay, hell yeah. So now we can kind of move on to the differentiation and then the integral process to get equations for velocity and equations for position. And the other cool thing about doing this process is when we get this equations for velocity or equation for position, like this, like experiment with these equations, because these are so cool, because like you can at any value of time you can find the velocity of the dog's hair. At any value of time you can find the position of the dog's hair. And then like even just saying that right now, it's like you can also point out like when these equations are no longer useful. Because anytime you have an increase in velocity, well, that's never going to change because it says it's constant. But you know what I mean? The dog's hair can't have a speed of light velocity. And you could say with this acceleration, at some point it is going to get the speed of light. So we just know that's, at some point these two equations won't be valid anymore. So I think that's also an important thing to kind of have in the back of your mind. I really didn't mean to say that, but also just know that for sure they're going to ask you to find the dog's length of the hair at 5 weeks. But just know you have a full equation here. You can experiment with putting in any value of time and getting the position or length of the dog's hair. Cool. All right, so now we're going to move on to the integration part. And we come back here to this equation for acceleration. Equation for acceleration is change in velocity, change in time. That's why I think this one is kind of the easier one just to say and see. Acceleration is change in velocity, change in time. You will need to use this one, to make it when you integrate, to make it kind of make sense. And so the process though is like, hey, especially when you just have a constant, and sometimes that can be even more difficult. Let's say acceleration was 0.924, t squared. Well, then, I don't know. It seems like that value throwing into there kind of makes more sense. And also, didn't we say this is acceleration as a function of time? So also, even doing this bracket subscript, just to know that this is a function of time is equal to the change in velocity. Acceleration is change in velocity, change in t. And we need, and this is a function over here. It just happens to be that this is just a constant. So I like to flip this, and so we have dv dt, and then we just put that constant right here. Okay, so the process goes is that you separate variables. And as I go, maybe I'll learn more, insert your own words, because, I don't know, like I should probably retake calculus. But, I think everyone only gets so much calculus at the most basic level. And that's where you're just like, what are we doing by separating variables? Like, can we come up with little problems to make these little steps make graphical sense and more sense? But anyway, so we separate. So the one way that I thought was very useful is like, hey, come back here again. If we say this is a function of time, it's also a function of position. I don't know. I don't think that is 100% representative by putting a t to the 0 here, but it can be very useful because when we separate variables, if we say t to the 0, if we separate variables, you're like, okay, this dt goes with this acceleration as a function of time. And if I have t to the 0 here, I know how to integrate. That's going to be t to the 0 plus 1 divided by 0 plus 1. And then we get t to the 1. And so that's kind of what we have. Okay, so the process is separate variables. So we'll have dv over here and then 0.924 dt. We're going to integrate both sides. Integration of dv just becomes v. And sometimes you'll just see it just written as v. But anytime that you can mentally kind of like, have an awareness that, no, this isn't just like a value. This is a whole function. You know what I mean? So that's kind of, and it's cool because we want to know the velocity at every time. That's very valuable to us. So we have, this becomes the velocity, and this integration, again, using the power rule of integration, goes t to the 0 plus 1 divided by 0 plus 1. Or if you have a constant, integration of a constant is just 0.924t, just adding a t on the end. Okay, anytime you integrate, we do have to have this constant, and this is the part where it's just like people might just neglect it, but don't, you know what I mean? Always put it in here, because this is kind of the fun thing to do. Anytime you integrate, I can definitely speak to this, is that you have to know something about what's going on. And, you have to know something, you have to know, like, at some time, you have to know something about the problem. So, and if you're going from acceleration to this equation for velocity, well, you must have to know the velocity at some sort of time, because that's literally the equation that we have. We have this right here is the value of the velocity when we input a time. And so, and some problems, you won't be able to input time 0. Maybe you know the velocity at the end. I don't know. Or maybe at the midpoint. Typically not. But at the very beginning, you probably know what the velocity is. And so in this case, we do have some velocity. So keep that in mind. So what we're going to do is we're going to put on this side of the equation, we're going to put this 7.28, and then we're going to, the time value is 0 weeks. And so you're going to have 0 here. So 7.28 is equal to 0 plus a constant. This constant has to be 7.28. And then rewrite the equation right away. So you get the full equation. This is the equation for velocity of the dog's hair as a function of time. You can throw in any time, and just remember this is time in weeks. And so that's where right here I wanted to go back and just double check. I don't mind not using units, because I swear if you put in units all the way through, you're going to make a lot more errors, like little errors. I mean, I think for me that's just a fact of life. But also have the double checks where you can go back and make sure to check your units. So this 0.924 was millimeters weeks per week. Cool. And then we're multiplying by time in weeks. So let's cross that out. And this value right here is millimeters per week. That's going to be our velocity. Okay, I'm satisfied. And then over here, we have this constant of 7.28. That also is in millimeters per week. So we have a check on reality for our constants. I mean, for our units. All right, booyah. So now we do the integration process again. We go back to our equations that say velocity is change in position, change in time. I like to flip this, when writing it. So I have change in position, change in time, dx dt. And anytime you use it, like don't say it dx dt. Like I swear, like my mind, that doesn't mean anything to me. I swear just basic differential equations are like almost meaningless. But if you say, hey, change in x, you know what I mean? And then say what x is, change in position, because this is always something, you know what I mean? Whether it's the change in sine x, you know what I mean? What's sine x? Well, sine x, sine of an angle, is a ratio. It's a ratio between the opposite over the hypotenuse. So say that. So just always say that. Say the change in the ratio. So if I have, and x in this case is an angle, but change in the ratio of the opposite over the hypotenuse, how would I say this? Change in position, change in time. Velocity is change in position, change in time. So yes, you don't add it and you don't say divided by. So derivative of sine x dx, or derivative of sine of theta d theta, is going to be the change in the ratio of opposite over hypotenuse, change in angle. Cool. And you can even do this. Hey, let's change the angle by 1 degree, or, what's my ratio going to change? And that's going to be that value. All right, hell yeah. So we have velocity is dx, change in position, change in time. And so our equation is velocity is change in position, change in time. So I'm going to write this dx dt over here, and then I'm going to put in the velocity equation right there. All right, so same thing, we're going to separate variables. So we know that velocity is a function of t. We can separate, and again, you know what I mean? This is where I need to go back to just basic calculus and make videos of explaining this process. You know what I mean? That's why calculus is easy, but just ridiculous, because you're just like, what are we doing? Like, what's the... and I'm going to make some more videos on integrals. Like, a lot of people think integration is area under the curve. Well, when I use integration, I don't know. I'm always thinking more average. Like, anytime I'm using an integration, I'm always thinking average, and I'll make videos on why that is. Anyway, so we were going to separate variables. Now we're going to have this dx, and then this side for our velocity equation. We integrate dx, that's a position, and this is a position equation as a function of time. This is t to the 1, so when we integrate, we get t to the 1 plus 1 divided by 1 plus 1. That's the power rule of integration, and so this becomes t squared. And then just don't forget to divide by 2. I forget all the time. I'm going to write any kinematic equation like this, and because that's why I brought this up here. Because if you write it like this, like these are our initial terms. This was our acceleration, 0.924. This was our initial velocity. And you're like, whoa, this is totally the kinematic equation where we have acceleration divided by 2, t squared, plus initial velocity, t. Now, our constant right here is going to be the initial position. Now, it doesn't say what the initial, and so let's get to it. So we just integrated, we have this constant. And so at time is equal to 0, hey, what's the length of the dog's hair? It's not said in this problem, so I just assumed it's 0. You know what I mean? Because we just want to know how much the dog's hair will grow more than whatever its current length is. So you could just say the dog's hair is X. I mean, you could put it in a value, you know, as a variable. But I just chose to say, hey, we shave this dog down, and the length of the hair is 0. And so at time is, so this constant, so if this is 0 over here, this term becomes 0 times 0. So 0 weeks here, 0 weeks here squared. Anyway, so constant is 0. And so now we have an equation for the position of the dog's hair given any time. We could throw in 1 week here, 2 weeks, 3 weeks, 5 weeks. Again, you could put in so many weeks that the dog's hair is a light year long. So obviously this equation, I don't know, just go Google the longest hairs. That's also good for physics problems, to find your upper end, to be like, hey, what's the Guinness Book World Records of dog length hair? And just know that if we're growing at this rate and increasing this rate, then that time value, I don't know, maybe it is 2 years to actually grow that long based on these parameters. But we know over time hair will kind of plateau. And so this equation is only going to be useful for so long. So always keep that in your playbook. But anyway, but mainly we have an equation for the position. This is going to be in millimeters. We'll get to the units in a second. As we input 5 weeks. So we have an equation. Always good to do this bracket and put in, you know what I mean? Because this is saying, hey, we have a position as a function of time. What that means is like, hey, we got a lot of stuff going on and then time. But it's going to pop out, you know what I mean, a position in millimeters. So that's general form of an equation. Something, something, time, and typically nothing else. I mean, if this was an equation as a function of time and I don't know, space, and we got into classic, I mean, relative, I mean, yeah, who knows? You know, I mean, we could do something cool, but it's not. And so it's just one variable, something, something, time, nothing else is changing with time. So that's very useful. Anyway, why I did that is because, you know what I mean, we're going to evaluate this at 5 weeks. So we can be like x parentheses 5, we can be like x parentheses 5, we can be like x at 5 weeks. So these are just helpful when kind of learning the language of how things are done. Because I swear, even from like high school SATs, when you get all this stuff, f of x and then f of 0, it's like you just lose your mind. I don't even know what that means. You know what I mean? And I kind of hate that. You know what I mean? Just the generic form of a function. I don't like it. I don't like the lowercase squiggly f. Anyway, so okay, so we do have this function of time. We're going to throw in 5 weeks. Basically, this divided by 2, 5 squared. And if we do all that, we get 47.95 millimeters. We're going to do a double check on units. We have, this was our acceleration. Alright, sorry about that. The camera cut out, but we're going to do a double check on units. This was our acceleration. It was in millimeters per week per week. Again, that's kind of how I like to write it. This value is in weeks, and we're going to square that. So we have 2 of these weeks downstairs. They're going to cancel both those weeks upstairs. And we're going to be left with millimeters. This was our velocity in millimeters per week multiplied by weeks. And we have a check that the units are in millimeters. Alright, hell yeah. So now this video sucked because I tried to do this whole process without changing the units right away. So I'm just going to include that. But I mean, we stick it out. We have a lot of errors, but we go back and find those errors. So it is still useful. I also kind of towards the end It is valuable because I also go over an analytical approach, and near the very end, I also show different methods on how to kind of guesstimate, get closer, do a graphical solution, kind of all that. So I think that's going to be a complete video, though. Yeah, like I said in the end, is just I never want to see this problem again because I just made the mistake of not changing my units right off the bat. And for whatever reason, I thought units weren't linear. I felt like if I had units, because they were tied in with acceleration or velocity, that I just couldn't change those to anything else. And that's basically what I learned from this problem is hell no. Units are linear. You know what I mean? If I'm saying this is 1 foot, then this is also 12 inches. You know what I mean? So I can, any number that has units, I can change. Now, you have to be careful if you have like a number that's where you have like millimeters squared, you know what I mean, and changing like square millimeters to square meters, you know what I mean. So that's the only, but you can, you know what I mean. There's still a method to do that, and so yeah, so that's what I learned from this video. If you can change all the units right from the beginning, and maybe change them to units you actually want, you could change this whole thing to units of, yeah, that would be a good challenge. Start this problem, instead of millimeters per week, change all your values to millimeters per day. And this is already in millimeters per day. Integrate everything, and then instead of getting a function where you input 5 weeks, you're going to input 35 days. You know what I mean? And if you didn't even like that, you could always, classically, you would want to change things to meters per second. And you just might have more intuition using meters per second. And then going through the whole process. And then getting a function, where t is in seconds, and then you would input, well, how many seconds are in 5 weeks? We have 35 days times 24, 35 days times 24 hours in a day times 3,600 seconds. So we would have 3 million seconds. So your equation is going to be ridiculous, and it's going to be hard to actually keep track of your significant figures, probably. But it could be useful to change the. I always like to work in meters per second if it makes the most sense. All right, so hell yeah. So thanks for joining me on this one. You can also watch the rest of the video. Alright, hell yeah. So we have Physics for Scientists and Engineers. This is Sarah Wade Jewett. You can find this on a PDF online, so that's pretty sweet. Alright, so we're going to try to do this problem using the most technical way possible, and then we're going to do the long format kind of like we always do. Sweet. So what we have is a dog's hair is growing, and it has a certain velocity of its growth. It's has a velocity of 1.4 millimeters each day. And so that's kind of, technically you would call this an average velocity. The first equation that I would write for velocity is change in position, change in time. You can also write it like this, dx dt. Now this is the derivative way to write it. It just means that your change, this factor right here is the most important. Your change in time is just really, really small. But this part right here, just don't forget that this might be, hella big, or, at least something. Or even tinier than your change in time. You know what I mean? And so this technically is slope. If I'm growing at 1 millimeter per day, we kind of have a slope of 1. If I was growing at a 0.5 millimeter per day, so we're going to take a change in time of 1 day, but we're only growing, 0.5 millimeter. So whatever units you have on this is going to determine kind of your representation of this. Okay, hell yeah. But I think this kind of gets kind of complicated. This is what we're going to be using for our technical solution. But if you just say kind of, hey, any change in time or any change in distance and any change in time, this is velocity as well. it's just average velocity. Sometimes this is an exact answer, but if your velocity is changing, it's not an exact answer. But sometimes I like to just think this is an exact answer because I'm satisfied with getting close enough to the right answer where I just really don't care for exact answers. So anyway, so that's where this is useful. But just know that this is average. This is the average velocity over that time. And even that, just because we average the velocity does not mean that this is a correct answer. It will be as long as acceleration is constant. And that's what we have for this problem. So let's get on to the technical solution. It says the rate at which the hair is growing, this 1.04 millimeters each day, will increase by 0.13. It'll increase from 1.04. We're going to add an 0.132 to the velocity, but we're going to do that every week. So yeah, so this problem is kind of tricky because you have like days here, and this says like, well, millimeters per day, but each week, you know what I mean? But all right, let's just get to the technical solution. The technical solution is also writing acceleration. Same thing, acceleration is the definition is change in velocity, change in time. And so I always kind of like to write it, you know, in two different ways like this. We're going to, and then we're going to say that acceleration, we're going to write that out, 0.0132 millimeters. Yeah, so it's millimeters per day per week. And here is why, you know what I mean, if you kind of follow how I write, so if we have like, hey, if I have something falling off a cliff, we know gravity is 10 what? Meters per second squared. If you write it like this, I don't think you're learning as much as you could be. You don't have an intuitive development or, you know, intuition of what the units are on here. If you write gravity is equal to 10 meters per second and then do this divided by second, this is a huge step up because now you can see this is going to be a change in velocity of 10 meters per second every 1 second, and you can just leave the downstairs the same. It's 1, but it's also for a change in 1 second. Okay, so that's what we have here. We have a change in our velocity of 0.132 millimeters per day, and we're going to have that change every 1 week. Okay, hell yeah. So now we can do kind of the integration solution. How we do this is we, like this is our equation that we're going to, you know, we're going to take this number and put it into this side of the equation. Cool. And then we're going to separate variables and integrate. So let's do that. So we have 0.132. I'm just going to drop all the units for now. And then we have dv dt. I think it's going to be easier. It's okay to write it like this, but I would flip-flop both of these. So we're going to be dv dt. And this is the step I would probably do right off the bat. Because you can say... it goes back to, well, yeah, just this equation. Acceleration is dv dt, and that's going to be equal to 0.132. All right, so now we can separate variables. And we can take a look at the units on this. Like it is going to be a change in velocity per change in time. We do have the correct units down here. This is change in time. So now, from the technical perspective, let's say the problem gave us like, hey, we're going to have an acceleration increase of 0.0132 millimeters per day per millimeter. You know what I mean? So every time the hair gets, yeah, see, yeah, that would be hella complicated. But yeah, you would probably, I would even need to make a separate video on that. But this would be a change in velocity per change in distance. So our acceleration And it's no longer it's no longer an acceleration. Acceleration is change in velocity, change in time. So if you had something like this would be a change in velocity per change in distance. That's all you could say about that. That would be change in velocity, change in distance. It would be a dv dx. So yeah, just kind of keep that in mind, but we're not going to worry about that. This is kind of your classic, hey, we're given the value, and it is constant. We're growing at a constant rate of 0.132 millimeters per day per week. Okay, so this is a function of time. That was what I was getting at. So we can write this dv. We can bring this dt up here. This is the process where you separate variables. So we have 0.132 dt. And sometimes in some of my videos I've said, well, hey, just make this a function of time. And what would that mean? So if we put t to the 0 here, now it looks like this is a function of time. Acceleration is a function of time. It's 0.0132 t to the 0. So at time is equal to 0, so how we would write this would be like acceleration at 0, or you could write this is another, I kind of need to make separate videos on this of just like, well, this is also t to the 0. I would write it like that, or you could just say acceleration at t to the 0. These are all meaning the same thing. But if we do that, acceleration at time is equal to 0, we're going to have 0.132, and then we're going to multiply 0. Oh, did I even do this right? Bummer. You know what I mean? Maybe you can't do this because 0 to the 0 is a nonsensical term, but if you have t is equal to 1, at 1 second, hey, accelerate, it's 1 to the 0. So this term just becomes 1. But anyway, when it comes to integration, I don't know. If you write t to the 0 here, it can help your integration, because now we're going to integrate both sides. And yeah, let's do that. So we're going to go dv is 0.132 t naught dt, and we're going to integrate. So integration of dv just becomes v. And this, we can use the power rule of integration. So we're going to have 0.132. We're going to have t to the 0 plus 1 divided by 0 plus 1. Sometimes it's really good just to write that out. Don't forget your plus constant anytime you're integrating. Alright, so let's simplify this. So we have velocity is 0.132. This is t to the 1. I'm just going to leave the 1 off, and we're dividing by 1. So hey, we're all set. And now it's plus a constant. Now, the other thing that's going to be very helpful is, like, what do we have here? We basically have velocity is something function of time. And we'll get to the constant in a second. So this is kind of what we have. So we have velocity as a function of time. So sometimes it's kind of useful to write it like this. Velocity as a function of time, 0.132 t plus c. Because now, when it comes to this part of the integration, anytime you integrate, it's different than differentiation. It's what makes some integrals impossible. Is well, if you have a polynomial, hey, you're in, and then you just need to know something about the initial conditions. You can integrate, but you need to know something about what happens. So for this problem, and let's see what we have here. So we have a velocity. Now, do we know something about the velocity? Hell yeah. It says the dog's hair's velocity is 1.0, so the velocity is 1.04 millimeters per day. Cool. And when is that going to be? Well, it just says like right now. So right now it's 1.04 millimeters per day. So that's where you would set that at time 0. So, you're going to set your clock, your stopwatch, and be like, hell yeah. So here's the two pieces of information we know. We know the velocity at time 0. So this is our initial condition. And what you would say is you could even say velocity at time 0 is 1.04. You could say velocity at t is equal to 0 is 1.04. So, and it kind of spells it out that you go back to this equation, where if you write it like this, it's very helpful. If you get to here and you're just like, I really don't know what to put in. like sometimes I remember be like, I don't even think this is an equation. You know what I mean? It's just, for whatever reason, it doesn't feel like an equation. But if you take this little extra step and be like, no, this is velocity as a function of time. Cool. And heck yeah. So we're going to have velocity at 0 seconds is going to be 1.04, and that's going to equal, so this side is going to be 0.132 at 0 seconds. So this whole term is 0 plus a constant. So we have to make this equation work. So 1.04 is 0 plus c. So c has to be, our constant has to be 1.04. Okay, hell yeah. So now we have our official velocity, or equation for our velocity. And this is the velocity of the dog's hair at any time, which is really remarkable. Alright, so we have 0.132 t plus 1.04. Okay, hell yeah. And but now we just know, like, at any given moment we know the dog's hair's velocity. And so that's just the first part. So let me rewrite this. So we have velocity as a function of time is 0.132 t plus 1.04. But we want to know how long the dog's hair will get in 5 weeks. We need to know the position of the hair. And so the equation for velocity is change in position, change in time. It's also dx dt. Cool. A small change, like a very incremental change in time, and then we're going to see how much, like this. That's the thing with differential equations. Yeah, sure, you're making this change in time very, very small. It doesn't mean that this is proportionally, the ratio, like the fraction here, will always be the same no matter how tiny you take this. It'll be more accurate as smaller as you get, but if your slope is like 2, if you have a change in 1 second, and then your change in position is 2 millimeters, well, sweet. Then let's do the same thing. Let's say your change in time is 0.1 seconds. Well, your change in millimeters is probably just going to be 0.2 millimeters. So this ratio is always going to be a ratio of 2 to 1. Cool. And technically what, derivatives are is just like you have to mentally think that this is a very small number. It's infinitely small, but that's where I think it's just horrible to think that it's infinitely small. I think you just lose all touch of reality. So that's where every time I see a dx dt, I just kind of give up. But if I can just say, hey, maybe this is just 1,000th of a second, and then booyah, we have a 2,000ths of a millimeter, and that ratio is still 2 to 1. All right, sweet. So this side of the equation, this side for that velocity is what we have right here. So we're going to have 0. Like I said, we should probably write it the other way. So dx dt is equal to velocity. This is probably the better way to write it, because this way when you write it and separate variables, you'll be able to have dx v dt, and then you can integrate and you can get a position equation right away. So we're going to have this dx dt, and then we're going to write in our velocity equation. So we have 0.132 t plus 1.04. Okay, now we separate variables. So we'll have dx, rewrite this, and then we have dt. Now this is like a parentheses here. I mean, if you wanted to get, and then we integrate. But yeah, it is parentheses. I mean, if you wanted to get hella technical, you could be like, hey, this is dx integration of 0.132 t dt plus integration of 1.04 dt. It's always kind of good just to, anytime you can do something a little bit different and it still makes mathematical and logical sense, it's good to work on those skills. Alright, so now we're going to integrate. This just becomes x, and again, it's an equation, it's an equation of position at any given time. Alright, and so when we integrate this, this is t to the 1. Sometimes that's very helpful. And again, it could be helpful to put t to the 0 right here, because this becomes 1.132 t to the 1 plus 1 using the power rule of integration. You know, sometimes I'll always miss this divide by 2 down here, so this is a very useful strategy for me just to go back to. All right, now we'll go over here, 1.04. But I mean, right here is just like, you know, for some it's just like, hey, I have a constant. Obviously, it's just going to be a constant times t. But for others, you know, you might forget that if you have a constant here, you might forget to do something with it. So if you have this t to the 0, I don't know, it gives you the ability to use that power rule of integration, even though I don't know if it's technically correct to do that. All right, hell yeah. So, and then we have plus a constant. So I'm just going to write this over here. So this is t to the 2 divided by 2. And I'm going to keep this term because this, you know, whenever you do something, sometimes you want to, you know, get it in letter form. And letter form, would, like this is still the acceleration. So you'd have acceleration, t plus... this is the initial velocity, you know, and then we're integrating dt, and then so we're getting 1/2 at squared plus v naught t. You know what I mean? So that's also useful, you know, anytime you're, you know, just using the numbers and not the letters, you can kind of see where the kinematic equations come from. So yeah, let's do this. So let's go 0.132. I'm just going to do this divided by 2 t squared plus 1.04 t. So now you can see this is the initial velocity, and you can still see that that's the acceleration. All right, now then we have a plus a constant. So what do we know about our position of the dog's hair? It actually never says that the dog hair is any length. So maybe this dog just totally got you know, buzzed in a couple locations, and so the hair is 0 length. So when we go over here, this is the position of the dog's hair, and so at time is equal to 0, hey, we're just going to say the position is 0 millimeters. So let's write that in. So this position would be 0. Cool. So, and I guess even that might be kind of confusing, where it's just like, hey, this is position at 0 seconds, that is equal to 0, and then we go on to this side of the equation. And I don't have room to write it, but if I throw in 0 here, this becomes 0, this becomes 0. So we have 0 is equal to 0 plus a constant. To make this equation balance, well, constant has to be 0. This has to be 0 as well. Okay, sweet. So now we have our equation for position is 0.132 squared t squared plus 1.4 t. And I guess the only thing that we need to make sure on this is the kind of the units, because our acceleration, now I even need to think about this. Alright, hell yeah. So I totally made a mistake, and that's why this problem is kind of tricky, because this acceleration term in millimeters per day per week, like the per week part kind of drives everything. So when we go back to like that first integration that we did, this is a velocity, and let's just think about this. This term is wrong. Our average velocity has to be, this was 1.04 millimeters per day. We need the average velocity in millimeters per week. So it would be very easy to do that. Just multiply this by 7. 7 times that 0.04 is 0.28, and then 7 times 1 is 7. So we're going to have 7.28 millimeters per week. Because when we took this acceleration term and said this was millimeters per day per week, let's see what we do to this. Yeah, I honestly I don't even know, I guess, but when we actually use this equation, it has to make sense. So the velocity and this time value is in weeks. You know what I mean? So because this this term right here is millimeters per day per week. So I should probably kind of slow down on here, but the units on this number right here is millimeters per day per week. The units on this number has not changed. And then when we multiply by time, we have to multiply by weeks. And when we do, we get millimeters per day. Okay, so this is pretty cool because I thought this was going to be wrong, but no. So I really do like making errors because it's very useful to find them without having to throw away the whole problem. You know what I mean? Go back to the place where you most likely thought you made the error, even if it's almost towards the beginning. But it's just a really good strategy. And then, checking units is like super important because even right here you got two, it's like polynomials. You know what I mean? Let's say you have a polynomial that's like y is equal to, 4x squared plus 2x plus 1. Well, let's say this is, you know what I mean, the number of the number of apple pies you're going to make for Thanksgiving. Cool. And I don't even know. But anyway, but I guess like the units on this has to be, because it's a polynomial, the units on this term have to be the same as the units on this term, have to be the same as the units on this term, because we have the addition of three different things, and that would be the units on this. So like number of pies. Cool. And so these must be, you know what I mean, like it must be, and that's a horrible example. All right, hell yeah, we can salvage it though. Let's make this polynomial 2x plus 1. So this is actually one of the pies that we've actually made, and this is what this is let's see. Oh, is the number of apples that we have, and each pie takes 2 apples. So this number right here is pies per apple. Pies per apples. No, that's not right. Holy hell. This video sucks. No, I mean, this is important. This is the same stuff we're doing up here. So let's just write this in. So this x term, let's say it is the number of apples that we have. So apples. So this equation is in pies. So we need to actually cancel this out. So we have apples. And then we need pies right here. So yeah, I was right that this is... I just don't know what this means. Like, let's say I have 4 apples. So I have 4 apples, and then I multiply by 2 pies per apple. That's all, because this 2 is just nonsensical. It would take a half an apple to make 1 pie. That's basically what that's saying. It says if I have 4 apples, I get 8 pies. So those are really tiny. Maybe they're just like just really, really small apple pies. Anyway, so that is a good strategy though. Like and that's why I'm doing this video, because we can work on some of the basics that are in chapter 1 that I think it overlooked, but for sure making sure your units are in check. And that was kind of just a fun way to start though. I took the units off for a reason, because I think it's important also to just kind of know how to separate variables, understand that this is a constant, understand that it was still a function of time, and so we brought in the units for that, and it wasn't a function of distance or anything funky. We were able to separate variables. It's just without the units, it's just really easy to kind of keep track of that integration process, but then at some point go back and check your units. So there you go. So this was millimeters per day per week multiplied by our time. But our time value, that's the only thing that we have to keep tabs on. It has to be in weeks. But they want the answer in weeks. They say, how much will the dog's hair grow in 5 weeks? Now, if they said 5.5 weeks, or 4.5 weeks, let's say 4.5, we can still, once we get to this equation, we can still estimate, because we would type in t is equal to 4 weeks, and then t is equal to 5 weeks, and then average the two. And because the acceleration is constant, the average between, oh, actually not at all, because if this is a this distance is gonna, it's not an exponential, but it's what do you call that when something's to the second power? So it's nonlinear for sure. So yeah, you wouldn't be able to average. So I'm glad I brought that up. Sometimes though, I don't care. Take the value before and the value after and call it good. Say the in-between number is close enough. All right, hell yeah. So we're almost there, and we have our equation for position. I'm just going to write this one more time, 0.132, 2. And let's get units on this. This is going to be millimeters per day per week. And, all right, yeah, I might have to actually double check all this. Oh yeah, we were not done double checking this. So let me get my velocity equation. That's kind of where we left this. Velocity was 0.132 t plus 1.04. So we still might be kind of messed up. This is units of millimeters per day per week. This is in units of millimeters per day. Okay, sweet. And then the time value is in weeks. So those two are going to cancel. So this velocity is in millimeters per day. Okay, and then let's follow the integration. We said this was change in position, change in time. And time is still in weeks though. So this is, so it's kind of fascinating where, yeah, I was right that you probably would want to change. Holy Toledo. No, because the velocity equation, when you multiply it by time, yeah, for sure, time has to be weeks. And then you're going to get millimeters per day, and then this is going to be in millimeters per day. But now, because time is in weeks, that messes us up right here. Because now when we integrate, we're going to have... we're going to have 0.132. This is still going to be in millimeters per day per week. Let's see what happens. And we're going to separate variables, divide by 2, and then multiply by t squared. Oh, maybe I'm losing my mind of what the actual integration means. All right, hell yeah, let's just go with it and see if we can catch our error. So when we integrate this is going to be 1.04 t, and our time right here is going to be in weeks. And so this has to be 1.04 millimeters per day. Alright, hell yeah. So I took a moment to think about this, and yeah, we're going to still keep on keeping on. But at the beginning, when we have this acceleration term of 0.132 millimeters per day per week, now this is where, just in general, when people talk about acceleration, I think you kind of lose your mind that it's like something technical, like you're just like, well, maybe I don't know what acceleration is. But when we... as humans, we drive cars and we have a really good sense of velocity. So when we have a velocity that says 0.104 millimeters per day, it's very easy to say, hey, I can change this to units of millimeters per week just by basically multiplying by 7, and this is going to be 7.28. So why can't I take 1.32 millimeters per day per week and then, you know, change it to, let's do that right now. So we're going to take 0.132 millimeters per day per week, and we want to change it to two things. We want acceleration in units of millimeters per day, and then we also want acceleration in millimeters per week. And we want it to make sense. And I think the best thing to do is just acceleration in millimeters per day, because then we'll have an equation where we can put in time, you know, as 1 day, 2 day, as any day, and get our position and velocity, you know, as a function in days. All right, hell yeah. So, and let's just do it. So we have to cancel out this week, you know what I mean? And then we have to multiply by basically a ratio of 1. So 1 week is 7 days. And since we multiply by this ratio, it doesn't change, you know, the value of this acceleration. So that's going to be 0.132 divided by 7. We get a not nice number, 0.132. Is that a fraction of any sort? So this is 33 2/50ths divided by 7. And then, so yeah, so we get, so this is, well, I don't know, let's just write it as is. I'm going to store that as our acceleration and change it to a decimal. So we get 0.0189 millimeters per day. So this is the rate of change, our velocity. Now this is pretty wild because humans just can't think of things that are really small. So a millimeter is like, you know, that's even too big. A millimeter is like that. That's even too big. But you can just imagine something going from there, like a very small, a very slow something, and it's a hair. You just personify it. Pretend it's like a Disney character or a Pixar character. This hair is actually a living thing, and it's moving, and it's just moving 1 millimeter. It takes a whole day to get to there, another to get to there. And so that's what we have. So we have a velocity of 1 millimeter per day, but now this is our acceleration. We're changing our velocity every day. So if our velocity starts out at 1 millimeters per day, tomorrow our velocity will be 1.0, you know, basically 2 millimeters per day. On the second day, our velocity will be 1.04 millimeters per day. So it'll take, so this is 1 day, 2 day, it's going to take like 50 days to actually have a growth rate of 2 millimeters per day. So this is kind of what that would say. And yeah, let's do that equation, because when would our, so if this is our acceleration, when would our velocity, and we're going to start at a 0, let's say our velocity is 0 millimeters per day. When, in how many days is our velocity going to be 1 millimeter per day? You know what I mean? When's that going to increase? And so how would we do that? So we got 0.0189 millimeters per day. And what do we want? We want 1 millimeters per day. So we got 1 millimeters per day. And so anytime you're working with acceleration, this term you can kind of just think of as like one thing. So we have a unit of millimeters per day, and then we also have a unit, and that's divided by day. And then we have something that we want. We want 1 millimeters per day. And so how do we get this value in days? Well, and this is where I use the example, especially if your brain can't handle anything more. Just say the units are the equation, and so we have these two different things, and you're like, well, what do we do to them? And I'm not going to write them again, but if I multiply this by this, well, this just gets squared, and I'm still dividing by time, so I probably don't want that. If I take this and divide it by this, well, then these will cancel, but then I'll have 1 divided by time, so I don't want to do that. So then but I think it's, when this is downstairs, it's like, well, how do I get that upstairs? We'll take this and then divide it by that. So I will write that. So we got millimeters per day. And then this is what we have. And then we're going to divide it by this. Millimeters per day per day. So the millimeters per day cancel, and then this time pops upstairs. So that's what we would do to the numbers. We would have 1 divided by this value right here, 0.0189. And, I got to get out of... and yeah, that's going to take 53 days. And that's what we anticipated. I saw that this was, because I saw this was 0.02 each day increase. And so I just imagined that it was 0.01 increase, and that would be 100 days to get up to a speed of 1 millimeter per day. And so it's going to take 50 days. And 53 was that answer. All right, hell yeah. So now we're going to rearrange these two equations. We don't have to go back to the very beginning. This time value is in weeks. And but this position, this value, also has to be in weeks. So we're not too far off, actually. So let's keep at it. So we have this position equation is 0.132 divided by 2, and it's going to be t squared. And I think we're satisfied. No, we're not satisfied with this either. I have actually no idea where the units are going to go on this one. So, but I thought if this was in weeks, I could do this. 1.04, and we got millimeters per day. And then I'm going to go 1 day divided by, or 7 days divided by 1 week. And so this divided by 7 multiplied by this time value in weeks, this would give us the right answer. But I'm not quite sure about this one. So what we're going to do is we're going to go back to the beginning, like I said, and change this to millimeters per day per day. Or, to check, we wanted to do the other way. We actually wanted to change this to millimeters per week per week. Yeah, let's try that. So we have 0.132 millimeters per day per week. Okay, so the week is chill. We want that. We do want to... maybe it'd be beneficial to rewrite this. So we have 0.132. Let's get millimeters on top. And then we have days right here. And then we also have weeks right here. So that's what we have. Usually acceleration is millimeters seconds times seconds times seconds down here. That'd be meters per second squared. That's typically what we have. Alright, but now we want to just get this units in weeks. So we're going to say 7 days is 1 week. Cool. And then this unit will cancel that unit. And now this times 7 is going to give us 0.132 times 7 is 0.924 millimeters per week. But this is pretty cool because we can actually go double check this and see how far off we were. So now this is our accelerate. Oh, and I'm sorry. This is millimeters per week, or 0.924 millimeters per week squared. So your kind of units on acceleration. Whoa, I did not expect this problem to run away with me, but let's do it kind of fast now. So if this is our acceleration, we're going to separate variables, and we're going to say velocity is 0.924 t. Initial velocity is going to be, and it has to be in millimeters per week, so our initial velocity is going to be 7.28. And so, did you see how I did that? I probably should slow down. dv dt is equal to this. We're going to 0.924, separate variables, integrate. We're going to get velocity is 0.924 t plus a constant. And so what we're going to say is at time 0, our velocity is But like I said, everything has to be in units of millimeters and weeks. And so this is millimeters per day, so we need to change this value to 7.28 millimeters per week. Cool. So our velocity is going to be 7.28 millimeters per week, 0 plus c. So our constant is going to be 7.28. So now our equation for our velocity is going to be 0.924t plus 7.28. Again, this is dx dt. We're going to separate variables, put a dt over here, and integrate, and we'll have our position equation is 0.924 divided by 2t squared plus 7.28t. And then our position at time 0, so we'll have a constant here, but if this is 0, our position 0, no, I'm sorry, at time 0, our position is 0. So 0 is equal to 0 plus 0, and then our constant is 0. So here's our equation for position as a function of time. Now we want to know, well, let's double check this. Well, let's just get the answer. So by how much will the dog's hair grow in 5 weeks? This value right here is not in weeks, it's in days. No, it's in weeks. Holy hell. So yeah, I totally forgot. We changed acceleration to millimeters per week per week. We changed this to millimeters per week, and now we're just set. So that was the learning lesson on this. Not to fool around with the units, just choose units and switch everything. And it's just fascinating how I thought there was something maybe non-linear about the units, but nah, everything is linear about the units. Going from millimeters to meters, we could have done that. Going from weeks to days, those are linear transitions. Okay, so we're going to put a 5 in here. So we have, let's just do it. And we're set. So 0.924 divided by 2 times 5 squared. So that's going to be 25 plus 7.28 times 5. And we have the dog's hair is 47.95 millimeters. It's also good in America. People don't really know meters, millimeters, even centimeters. But my conversions are that, I think the easiest and simplest is that 100 millimeters is 4 inches. I just think like mountain bike suspension in the 90s, like 4 inches was pretty darn substantial suspension, and that was like 100 millimeters. And so if you're into mountain biking, if you have 150 millimeters, hell yeah, that's 6 inches. If you got like 175 millimeters, well, that's going to be 7 inches. So, and I don't know, just the fact that millimeters is so precise, it's actually exact. 25.4 millimeters is 1 inch. I think it's good to also melt your mind and be like, hey, let's not make this precise and just pretend that this is a pretty exact ratio. 25 millimeters is 1 inch. So then it's just going to be easier. If you know that 25 millimeters is 1 inch, then you can see this is about 2 inches. So that's going to be 2 inches of growth in 5 weeks. Even humans, we don't really use weeks unless, if it's for babies and stuff. So, about a month. So we're going to get 2 inches in a month. So always change the problem into units where it makes sense, where if you just say it, you have like just an instant picture in your head. Hey, this dog's hair is going to be 2 inches in a month. So in America, that makes a hell of a lot of sense. That will be visual. Alright, so now we're going to go back and double check this answer and just see how far off it is. But we can actually see how far off it is from here because we'll have, I don't know, 1.04 divided by 7. Yeah, this one's just way off. But maybe we switched. Yeah, I don't even know what we did. Millimeters per day. No, we switched this to weeks. So this is going to be 1.04 divided by 7 times 5. No, that's still not going to, that's still horribly off. Yep. Oh man, this is a good problem because if you go down a wrong path, you'll just melt your mind, like, because the units just get totally mixed in and you don't even know where they go. Yeah, that's wild. I'm kind of curious. Yeah, I don't think you can do anything about it. I mean, we could try again. So 0.132 is our acceleration. So that means our velocity equation is this t plus our constant, but this is in units of millimeters per day per week, so our time is in week. So we would switch this one right away. 7.28. This is going to be in millimeters per week. But then when we go to integrate again, this is millimeters per day per week. But maybe that doesn't matter. Like maybe even right here we're already in weeks. We change this to weeks, and this, even though this is millimeters per day per week, maybe when we integrate again, it doesn't matter. But does it? It seems like it does, because our actual answer was 0.924 divided by 2. So this was 0.462, and we're just not going to get that. If we integrate this again, yeah, so I apologize that I don't know where, like, if it's even possible to mesh units when you do the integration twice. I know just to do the integration once it was fine, because this is in millimeters per day per week. And, well, no, this does not work, because if I throw in weeks here, this is going to give me millimeters per day. That's going to give me the velocity. But then over here, I change this to millimeters per week. So, nah, this doesn't work. This has to be 0.14 millimeters per day. Now that works. 0.132 t plus 1.04 millimeters per day, where you throw in a value of weeks, gives you millimeters per day. So it's a velocity in millimeters per day when you input a time in weeks. But like right here, I just don't think you can do anything because this time value is already in weeks. If we want to continue the integration process, we need to get these constants in terms of weeks. So let's do that again. So this is going to be 1.32 millimeters per day times 7 days per week. This is going to be a multiplication of 7, and hell yeah, you get that 0.924 t. Cool. And then when we integrate, that's going to be, that term. This term over here is in millimeters per day. We want to go 0.04 millimeters per day, 7 days per 1 week. So this is going to be 7.28. When we integrate this, we're going to get a t. So, yep. So there you go. You can do the integration process once and still hang on. But at some point, the second you integrate, you're going to choose your value for t. And that's going to drive your second integration. So I'm glad I walked through that to be like, well, what part of that is going to be kind of wonky? All right, hell yeah. And now we just need kind of it's always good to go back and kind of get a check on reality. So if we wanted to get a fast answer, just within a factor of 10, we're going to have an increase in, the hair is going to grow at 1 millimeter per day. So that's going to be the easiest thing to guess, 1 millimeter per day. And how long will it grow in 5 weeks? Well, I don't even know. It's like, I know in a month that's 30 days, and then times, there's 37 days in 5 weeks. And we're growing a millimeter a day. So I'm just going to, first guess is 37 millimeters. But I know that our growth is going to be increasing. So then I just focus right on this term. Let's say this is just 0.1 millimeters per day. So this is going to be the increase in speed. And again, it's kind of useful to maybe start with a velocity of 0 millimeters per day. but our velocity is going to go from 0. The next day it's going to go to 0.1, then 0.2, then 0.3. Oh, okay, so it's going to do that every day. So we're going to do that for 37 days, and that means we're going to have a velocity of 3.7 millimeters. Holy Toledo. Yeah, that's right, because if I did this for 10 days, I'm going to have a velocity of 1.3. But I'm going to round this to 0.1, and so in 37 days, our velocity is going to be 37 millimeters per day. But now I know that the increase was like that, so that's where I break out, this driving analogy. If you're going to start at 0 miles per hour and then slowly ramp up to 60 miles per hour, because it's just kind of it's a nonsensical one, like no one's ever going to do that. And let's say you did that over the course of an hour, you can see just very easily that your average speed is going to be 30 miles per hour, and you can figure out your distance. 30 times 1, you went 30 miles. So the same thing here. If my velocity, this is going to be 3.7 millimeters per day, is going to be right at the time where I measure the hair. I started with 0 velocities, so kind of the halfway point, I'm just going to guess, is 2 millimeters per day. Sweet, so that's going to be my average velocity, and I did that for about 40 days. So, so in this case, I'm going to have a velocity of 2 millimeters per day for 40 days, and looks like my hair is going to grow 80 millimeters. So, that's kind of, and I don't know why that number kind of ran away, but that's one way to do it. Then you can kind of get a little bit. Oh, and I'm sorry, I read this wrong. No, this says the. I have a hard time reading things. I kind of just, in my mind, kind of make up what I think it should be. But I mess up all the time with that reading comprehension. This is an increase of 0.1 millimeters per day, but this is only every week. So the rate at which the change in velocity of the hair, and it's so weird to think that hair has velocity. That's kind of the take-home point of this problem, is to be like, hey, let's say your hair is actually a car driving down a road and it's just super slow. You know what I mean? It's just bizarre to think of hair as something with velocity, but that velocity is increasing. And so back to our guess, which was, I was wondering why that was an overestimate. So still, I'm going to go from 0 to 0.1, but every week I'm going to do it. So I'm going to go 0.1, 0.2, 0.3, 0.4, and by the 5th week I'm going to have a velocity of 0.5 millimeters per day. The average would be 0.25 millimeters per day. So that's the average velocity from that. Now we know that we're starting with a velocity of 1 millimeter per day, so this average, so that's the other way to look at this. You could say, hey, let's say I start at 30 miles an hour and I go up to 60. So this is 30, this is 60. Now what's my average velocity? Well, it's 45 miles per hour. So it's always good to have some sort of very simple graph, because then you can throw in kind of the problem. It's just like, hey, this is 1 millimeter per day velocity, and then up here is 1.2, no, it's 1.5 millimeters per day. So then you can easily see that my average velocity is 1.25 millimeters per day, and we're going to have 1.25 times 37. And that gets us fairly close, 46.25. Obviously, there's another third here. So another way to estimate it is like, hey, we're going to have an increase of the velocity is going to increase by 0.1, 0.2, 0.3, but every 3 days it's actually, you know what I mean? So if we have this increase from 0.1 to 0.2 to 0.3 to 0.4 to 0.5, it's actually more. It's actually 1.3, 2, and so by this day it's actually going to be 0.4, and then by this day it's going to be 4.3, and then 4. So we're going to 5.3, and then 5.3, and then this would be 6.6. So that's a better estimate, and now we'll use that. So we're going to go from, and I don't know where I got This is going to be 0.5, 0.53, 0.66. So now we're going to have a velocity from 1 to 1.66. Average is going to be 1.33. So 1.33 times 37 days. And we're getting closer, 49.21. What was our actual answer? Our actual answer to the problem? I don't even know. Actual answer to the problem was 47.95. And so what we did is we just kind of went over like some guesstimates, and we got 49.21. So heck yeah, we're kind of honing in on that right answer. So I would have done that at the very beginning, but I thought I was going to really nail this one, just starting from the integration perspective. Alright, and I feel like I do not want to ever see this problem again, you know what I mean? So, but we'll see. So let's do a graph of it, you know what I mean? Because after, that's the thing, is like you can solve a problem just kind of using your intuition, using integration, and then graphically is probably the way that no one wants to do it, but we had this example of 0 to 60, and then how this is more like starting at 30 miles per hour and getting up to 60, finding our average velocity, and that was important. Because if we know our average velocity and we know our time, hell yeah, we know our distance. Distance is average velocity times time. Like that's kind of what we're honing in on. So the graphical nature of this would be, we would just have that graph, you know, and then so we have this, and then we got 1.04. We're going to split this up into 5 weeks, and now we'll totally get a very accurate answer, which will be the actual exact answer. Okay, so every week this velocity is increasing by 0.132. So, and we're not even going to use our calculator. So we got 0.132. Adding these together, we get that. So right here we're going to have 1.172. And then we're going to add 0.132 again, 4, 10, 3. Right here we're going to have a velocity of 1.304. Let's keep going. And what you should be seeing is like, we don't need to do this. I mean, you could. So like right now, like the second you see a pattern, be like, oh, okay, I just need my velocity up there. So like even like right here, like my brother does all this the time in middle school. He'll have his students like, hey, he wants his students to like tackle a problem from a bunch of different angles. And so I use a method of like, hey, do something actual. If you do this repetitively, you'd be like, well, I never want to do that again. Or you can be like, what pattern did I see? And could I have just gotten to the answer? So the velocity up there is going to be 1.04 plus 0.132, and then 1, 2, 3, 4, 5 times 5. And I like this, where there's no units on here. You just kind of intuitively know what to do with the numbers. 1.04 plus 0.132 times 5. Because this, even though this is a simple problem, this is the same setup that you will use to do complicated problems. Just the other day I was doing a gravitational problem. It's the rod with the bead, and the earth is down here. Both are falling and the bead separates. But you can't integrate. The force or acceleration equation is gravitational constant mass of the earth distance squared. And so your acceleration dv dt, but you have an x here, you know what I mean? So that was kind of fast. You can do it one time. You can use chain rule to go dv dx dx dt, and then you can see this is dv dx, and this is velocity, and then you can have these terms that are, when you separate variables, those terms separate, and then you can separate this over here and integrate. You can only do that one time, because then you're going to get, you can't do the chain rule kind of twice to get a position equation as a function of time. And that's too bad, and it just shows you the fact that integration is kind of a tricky beast. But But it's from this problem that I solved just by using this analogy. And the difference in acceleration was so small that this initial value of speed was all you needed for that problem. So even this is just like, well, that's the first thing you should do on a problem like this, is just like, well, let's see. If my velocity of my hair is 1 millimeter for 37 days, booyah, it's going to be 37 millimeters. But then if it says, hey, but the velocity is actually slowing down because it's becoming summertime where a dog's hair slows down, well, then I at least know my answer is going to be less than 37 millimeters. And so that can be useful. This is speeding up. So now you have to figure out by speeding up by what. And it's not even that appreciable. You know what I mean? We said in 5 weeks, it's just going to go up to like 1.5 millimeters. So even at the top end, and let's say you mistakenly just thought that was the velocity, 1.5 times 37, you would get 55 millimeters of growth. And, you know what I mean? Who cares if 55 compared to 37 millimeters? I mean, cool, your dog's hair is going to be 1.5 to 2 inches. I mean, it might not even be very visible. So that's kind of tackling a problem for just the standpoint of, can I get an answer? And when you got something like this with gravitation, you're just like, well, don't worry about the nitty details. Can you figure out like what your acceleration is? And, you know, consider it a constant and change that velocity. I don't know. So that was very helpful for that one. So let's use this equation, 1.04 plus 0.132 times 5. And we got 1.7 up there. So now let's continue just adding this this change in velocity, 0.132. So we got 6,341. So we got 1.436. And let's do it one more time. 8, 6, 5, 1. 1.568. Okay, hell yeah. And now we can see, like, yeah, these values were unnecessary, but they were necessary if we were just trying to get there. You know what I mean? If this was my prize, and be like, okay, now that I have that, I can figure out the average value. And even these problems, it's like, because people get hung up into like the calculus and the differential equations and all that jazz, you forget the simple details of like, hey, what's the average velocity here? And it's the average between these two numbers. And I swear, I graduated without knowing how to take the average between two numbers. You know what I mean? Especially when you're doing linear and interpolation, trying to find the average between two things on a graph, you're just like, how do I not know how to take the average of two numbers? And it's just adding them and dividing by 2. It's really wild that equation, is, what do they say? Yeah, underestimated. So we got 1.7 plus 1.04 divided by 2. So this gives us our average velocity of 1.37. Now this is all we need now. We have 1.37 millimeters per day, and we got 5 times 7, that's 35 days. Oh, holy hell. I was saying 5 weeks was 37 days. So hopefully you caught my error there. That's horribly wrong. 5 weeks is 35 days. My bad. Anyway, so we have 35 times 1.37 times 35, and we get that 47.95 millimeters. And that is the answer we got from integration. And I really, I refuse to do a problem where you can't tackle it 2 different ways. Or that whenever I get a problem, I'm always thinking, hey, can I just guess? And then while I'm doing it, is there like 2 different ways I can approach it to match my answers, especially when it comes to matching exact answers? Because now I can just, now you can still, like with this gravitational problem, you know, if you do something like this and kind of simplify it, your answer is going to be wrong. I mean, because it's very difficult. Because you can't do the integration, you have to use an approximation method. Let's say I set it up in Excel, and you're just going to get an approximate answer. It might be within a factor of, you know what I mean, like 0.1% error. So you might be like, hell yeah. But that's also, I'm basically saying, like, even if you tackle a problem from two different ways, you might be making a single assumption that makes both those answers wrong. So yeah, so it is helpful to tackle a problem from two different ways, but just be aware that that sometimes isn't a indicator of certainty, just because you're popping out the same answer. All right, hell yeah. So now I officially did what I wanted to do with this problem. I think I'm going to put kind of a short at the beginning of it, because this was a good one. It's fun to kind of get messed up on a problem and then, like, not lose your cool, not have to go back to the very beginning and scratch it all out again. So hell yeah. Thanks for joining me on this one, and that's a video.